Welcome back to class 15. Here's another example. This is example 5.9 out of Cengel. Excellent book. I highly recommend it. You should buy it. And we're going to use US units. Consider an ordinary shower. I will. I'll take a shower tomorrow. Where the hot water is 140 degrees. It burns. And it's mixed with the cold water, 50 degrees Fahrenheit. If it is desired that a steady stream of warm water at 110 degrees Fahrenheit, I don't think that's hot enough for me, be supplied. Determine the ratio of the mass flow rates of the hot to cold water. Assume the heat losses from the mixing chamber to be negligible, so it's kind of insulated, and the mixing to take place at a pressure of 20 degrees Celsius. No, Fahrenheit. Oh no, I said Celsius. I said, I'm losing it. 20 psia. All right, yes, it's my brain getting mad at me. So anyway, we're gonna go 1, 2, and 3. Great. And we want to find, well, you know what? Let me go to in our book. This is not Cengel's book, but table F7.1, or this is out of Bornacki, and we'll look at 140 degrees Fahrenheit, and we'll find the enthalpy of the liquid, right? The fluid. So this is the low end of the thing. So it's not at the 20 psia, but it's an approximation. We're saying that the enthalpy is about right there. The same thing here true for 50 degrees Fahrenheit, HF. So I should say that this is going to be H1 right here, and then this is 18.05 BTUs per pound mass. And that's going to be the H2, and then at the 110 degrees Fahrenheit, you get the fluid enthalpy of 78.01. And you can look this up yourself if you want to double check that I got it right. It does vary in some books. Some of them do, I'm not sure. So anyway, if we're looking at a mixer, right, this is really what we're coming back to our fundamental conservation. So this is the conservation of energy equation. Conservation of energy. Heat rate minus work out. So this is heat in, work out. Here is summation of all the mass flows with the enthalpies coming in. Summation of all the mass flows exiting and the exiting. But if he's insulated, there's no heat transfer outside of the drawn control volume. There's no work crossing the boundaries. So all we're left with is M1.H1 plus M2H2 minus M3H3, right? Now we can also use the conservation of mass, which is going to say that all of the, you know, if you go to the summation of M in dot minus summation of M dot out, right? Or for us, M dot 1 plus M dot 2 minus M dot 3. And therefore, M dot 3 is equal to M dot 1 plus M dot 2. And we can go ahead and place him right into there. So, saying that, you get M dot 1 H1 plus M dot 2 H2 minus M dot 1 H3 minus M dot 2 H3. All right. So we don't know the M dots, but we do know that we want to find the ratio. So let's define. So define a ratio, which we call Y. We just gave it a letter, M dot 1 over M dot 2. because it was asking for determine the ratio of mass flows of hot to cold. All right, so hot to cold, hot is 1, cold is 2. So what we could do is we could divide through here by m dot 2. So you go m dot 1 over m dot 2, h1, plus h2, right? Because we divided, or I could write it out. I don't care. I already was being very slow and pedantic. Minus m dot 1 over m dot 2, h3 minus m dot 2 over m dot 2, h3. Well, that goes away, and that goes away, and that becomes y, and this becomes y. So what we could do is we could write out and distribute the thing out a little bit and go y is equal to h3 minus h2 divided by h1 minus h3. Can you see how that was done? Did I skip too many steps? I don't think so. And here's h1 times y, right? That was h1 times y. And there's h3 times y was minus, right? And yeah, okay, so this works out. So anyway, we could go ahead and write these out. 78 point, let's see, we'll try to see if we can get the others up there. All right, start out with h3, which was 78. 78.01 minus h2, which was 18.04, 18.05, excuse me. And then h1, which was 107.96, it's the hot water, minus, and lastly is h3 again, right? So that was the 78.01. And we get 2.002. Yay! Okay, so this matches what the example that was in Cengel. I want to point out though that these are no phase changes are taking place. So we can alternatively, or because there's no phase changes, we go Cp delta T over Cp delta T. But notice the CP's would cancel out. So you could just take the temperature differences, right? You could just take 110 degrees, or let me write out the numbers here. We had T3 minus T2. And then we had T1 minus T3. Or 110 minus 50 divided by 140 minus 110. And what you get is exactly 2. So that versus that. But just recognize that you can make sometimes you can make if it's a no phase change, you can make a simplifying thing. And when it's the same materials, the same water, lake water versus the tap water, they'll have the same specific heat, so you could go ahead and just use them in that way. So it was a simplifying assumption, but not to be used if there's any type of phase change, or if the liquid or fluid of whatever it is does not behave linearly and is very sensitive, or is in the range where it's sensitive to specific heat, where specific heat is not constant.